Hi everyone, I'm Monbroussou. I'm a PhD student in Leipzig, in Sorbonne University, and also in Naval Group. And today I'm going to talk about a recent work of mine about a new scheme for photonic architecture, which is named state injection. The goal of this presentation is to give some kind of motivation for trying to go from from the algorithm side, from the design of the algorithm, and trying to investigate what are the good architecture that fits well for quantum algorithm and in general quantum machine learning. So first thing first, those are the co-authors for this paper. You have the archive link if you want to take a look. So there are people from quantum machine learning, including myself, photonic algorithms, and photonic experimentalists. So it's a collaboration between mainly Leipzig and INRIA. I will try to give the motivation as we thought about this topic. For people like me and Elliot, we try to design quantum algorithms for quantum machine learning purpose, and we try to do it for near-term algorithms. So if you want to design quantum machine learning near-term algorithms, you need to face many challenges, and the main one are highly theoretical. First, you need to make sure that your method cannot be dequantized, so there is no classical simulation or approximation method to do exactly what you are trying to do with a classical computer, which is an important part of the quantum machine learning field, so you need to be aware of what the community is doing to avoid all those results. You need to make sure that the algorithm that you're creating has good expressivity. So basically, it means that it works, and more than it works, it's not only working on Qiskit for time model, but it will be working for It will be working for industrial problem and for larger scales. And finally, especially for neural networks, you need to make sure that you have theoretical guarantees on the convergence of your algorithm. So if you have neural network, you need to make sure that you will not have any vanishing gradient phenomena. And so you could ask, but what about energy consumption, hardware requirements, noise, and practical problems that you could have with quantum computer? And usually, quantum machine learning people, or many of them, including myself, we first design the algorithm only thinking about those theoretical points. And the reason why is because it's incredibly challenging to find near-term algorithms that tackle all those points. So at first, I will explain how we have theoretical tools to avoid problems with those 3 points and how we adapt them for actual experimentation. So the method that we use is to consider subspace-preserving circuits. And subspace-preserving operation preserve symmetries in the quantum state that you're using and allows you to consider sub-Hilbert space of smaller size. So, for example, let's take this gate, the RBS1. So let's say you only use this type of gate, which is a match gate, but even more particular. It preserves what's called the Hamming weight of the states. So the Hamming weight is like the number of 1 in the bit string. If you use only those type of gates, the equivalent unitary will be block diagonal, and each block represents one subspace which is independent from the other one. Meaning that if you start from a state of a fixed Hamming weight, let's say K, you will only have to consider the unitary matrix WK, and you can do all the computation with this unitary. So it's bad in terms of simulation because you could say, okay, it's easier to do the simulation of the algorithm. I can only try to simulate the block WK, and the size of the block will be polynomial with the number of qubits of degrees the Hamming weight. So basically, the large block will be exponentially large, and the tiny block will be polynomially large. So it could be a bad idea. But the reason why we are doing this, is because when you are considering polynomial size subspaces, you have a bunch of theoretical arguments to show that you will have good training and nice properties. And if you're using large block, exponentially large subspaces, you will have bad training, vanishing gradient phenomena, and it will be very hard to design a quantum machine learning algorithm that will work and that will scale well. So we have our strategy. We will focus on subspace of polynomial size, and we will focus on polynomial advantage. And so now that we have our strategy, we want to choose an hardware to do experimentation and to go closest to the practical implementation. So, first, sorry. First, there are already a bunch of algorithms using this strategy, including algorithm to do quantum transformers, to do quantum orthogonal neural networks, and more recently, we propose a work to do quantum convolutional neural networks. So all those work have the same strategy. You consider polynomial size subspace, and you try to mimic classical machine learning architectures. And so only considering the last example, but it's true for all of them, the idea is you avoid dequantization results by using the subspace preserving properties, by using measurement-based tools and certain type of encoding. You avoid vanishing gradients, you avoid a convergence issue because you use subspace preserving. And you ensure that it will be useful for large problems because you just try to mimic what classical ML is doing. So you know that it will be useful because it could be useful because if you can just take large ML architecture and replace part of them with those building blocks. So it's a strategy that pass the sanity check of dequantization, trainability, and expressivity. Now that you have your quantum algorithm, you know that you have complexity speedup, you know that you can have polynomial advantage even of large degree. But the issue is that now you need to compare with classical machine learning algorithm. And it's kind of hard because even if on the paper you have better complexity, complexity is not a good argument to compare quantum algorithm and classical algorithm. You need to compare the speed. Especially if you compare with GPU method, because GPU parallelize the computation, so it's not super fair to only consider complexity. So you need to compare all the QPU layers with the GPUs in terms of speed, but also for different figure of merit, such as energy consumption or security. So once you have your strategy, you need to think about hardware to do the computation. And one hardware which is subspace preserving natively is the photonic one. So if you consider, for example, if you consider linear optical circuits, it preserves the number of particles of the circuit, right? If you start with a state of a given number of photons, the output should be of the same number of photons. So it's kind of the definition of subspace preserving. And you can represent such circuits as infinite size unitary, which is block diagonal, and each block represents a number of photons. So you could just choose to fix a number of photons according to the number of modes, and the degree of the potential polynomial advantage will be given by the number of photons. Another good thing is that if you consider low number of photons, you have a low polynomial advantage, but you could say, okay, but because I use less photon, I can generate my states with higher rates, which could be nice for trying to beat GPUs in terms of speed. The big issue with photonic platform is this photonic homomorphism, which is the base of boson sampling. So the thing is, all the subspaces, all the blocks WK are perfectly determined by the first one, W1, meaning that if you try to generate any unitary matrix WK, you cannot, because each coefficient are a weird permanent relationship from coefficient from W1. And it means that the set of matrix WK that you can reach is of the same dimension of W1, so basically you are really restricted in what you can do with those subspace. So the idea is that you are very happy to use photonic architecture because it's subspace preserving and it could be very fast, but you need to break this photonic homomorphism. One way to go beyond photonic homomorphism, which is used if you want to create qubits with linear optical circuits, is to use some type of measurement-based operation and adaptivity. And the main one is feed-forward adaptivity. So the idea is you say you have your a linear optical platform. You just put your beam splitter, phase shifter, and at some point you will measure part of the mods, and according to the measurement outcome, you will change the rest of the chip. And if you do this, you can go beyond what the photonic homomorphism offers you. But the issue is that you need to make all the photon on the remaining mods to wait, at least during the time where you change the following parameters. And because usually it's thermo-optical effects, it could take some time up to 1 millisecond. Our proposal is very simple. Instead of adapting the rest of the chip, we just propose to inject new states, and the choice of injection depends on the measurement outcome. So it's still an adaptivity scheme, but it's not about changing beam splitter or phase shifter, just preparing states and putting back in the computation. Because you can use only fast linear switches to do so, you can reduce the time, the delay for the other mods, and so it could be experimentally easier to do so. The good thing also for us is that if you choose to inject states with the same number of photons, it's still subspace preserving. You can say, okay, I measure a given number of mods, a given number of photons, I re-inject the same number, or a superposition of the same number, and you preserve the number of particles. So it's good because you can do subspace preserving quantum algorithm and go beyond photonic homomorphism with a scheme which could be experimentally easier. In the paper, we gave a bunch of theoretical reasons why it's good, because you're no more considering linear processing. It's no more unitary because you use a measurement-based operation, so you need to focus on the states. And basically, we explain how it's good in terms of degrees of freedom of the states, meaning that the set of states that you can reach using state injection will be of higher dimension. So in a way, it means that in the state space, the potential states that you can reach, they can go in more independent direction. And so if you compare only linear optical circuits and with state injection, every time you use state injection, you can add many degrees of freedom and you can achieve more complicated states. So finally, in the paper, we also discuss for other people, because we have a strong focus on quantum machine learning, or at least I have a strong focus on quantum machine learning. But you can also use this scheme to do other type of quantum algorithms that are very hard. And one of them is probability estimation. So it's known from a paper from Ulysse Chabot that if you try to know the probability of measuring an output state S from an input state T, it is believed to be exponentially hard. Okay, exponentially hard in some cases. And so it could be a very hard task to do using feed-forward adaptivity, and you can do exactly the same with state injection. So you can say, okay, if I want to know the probability of measuring a state S from a state T, knowing the outcome measurement, it could be very hard. And in both cases, the part of like the regime where it's very hard to do classical simulation of this problem are in the same box. So if you consider enough measurements and if you have enough photon measured during the measurement, then there are some regime where it's believed to be exponentially hard to do the probability estimation. The only change is R is the number of photons that you need to measure during the computation. So if you're using feed-forward adaptivity, it means that in the beginning you need to have a very large number of photons. For state injection, you can start with a lower number of photons and just inject additional photons during the computation. So in a way, it could be experimentally easier. Our goal was at first to show new architecture using state injection and to show that you can, create a new equivalent of KLM scheme using state injection, but it's ongoing work. But at least we show how you can have theoretical arguments that you can use this proposal, experimental argument why it could be easier, and some example of very hard algorithms that you can do. So now the the work that needs to be done is basically resource estimation. We need to adapt all those subspace preserving quantum machine learning algorithms to use those schemes that are very experimental and try to understand how it affects the time, how it affects the energy consumption, how it affects even error correction, because you put a lot of structure on your state, so maybe you can adapt the error correction codes. So it's still ongoing work, but I think it's important. It's very important, especially for people like me doing quantum algorithm, to understand what are the figure of merits for experimentalists or people working closer to the hardware, and try to adapt the algorithm to those points. So if you have any question, I will be very happy to answer.
Thank you, Leo, for the talk. You showed a picture of a very talented experimentalist at the beginning. I'm wondering if there's an actual experiment going on with this, or is this a plan?
No, there is one. So when I said there are a bunch of subspace preserving quantum machine learning algorithm, we try to do an experimentation of the QCNN using linear optics and not state injection, but like simulation of state injection on linear optical platform with Fabio's kernel.
More questions for Leo?
I guess it might be a bit far-fetched, but do you see any link between the subspace preserving QML and this Krylov subspace method?
Honestly, I'm not. I don't know.
Okay.
I have no idea.
Okay. Well, we can talk about it later.
Yeah.
Thank all the speakers.